Dear student, let us begin the lectures on machine design part 1. This is lecture number 39 and the topic is design of brakes. Now, there cannot be any doubt that brake is one of the very important members of a machine. The brakes are used normally to reduce the speed of some moving components, that is to dissipate the kinetic energy of a moving system to some other form of energy, for example heat. Normally this is heat. Now, there is a very similar component in machines. Normally this is called clutch, but the difference is that in the clutch the two moving parts are brought into synchronicity, that is the speed of two parts are brought to the same, and in the clutches the two parts are both of them are moving, whereas in brakes one part is normally kept stationary, but in both the cases the energy is transferred from one part to the other by means of frictions. So, here in this members, brakes or clutches, the friction force plays a dominant role. So, friction force is a very complicated force, and normally it is modeled to be a Coulomb frictions, where the friction force is proportional to the normal force applied. So, this is very much known to you that how to model a Coulomb friction force, but normally let me point out that in typical situations the friction force, the modeling of friction force is a very complicated task, because the friction is a microscopic phenomena, and in order to bring it into the macroscopic scale, then many assumptions are to be made. So, normally we make these assumptions named after Coulombs. So, we shall use the Coulomb's law when to model the friction force. Now, let us begin the lectures on the design of brakes. This is the first part of the lecture and to be concluded in the next lecture. Now, first of all, let us come to classification of brakes. What we see here, there are different kinds of brakes. One is the hydraulic brake. There are few examples, for example hydrodynamic brakes, pumps, etc. Electric brakes, eddy current brakes, generators, and so on. Now, these two kinds of brakes, they cannot bring the moving body to complete rest. So, what it can do is to bring the speed of a moving component down to some limit, and normally very high power, that is a very high energy moving parts are brought to a low speed level by means of this kind of brakes. So, they are normally used in trains or trams or locomotives, etc. Now, mechanical brakes, what we are going to study in these two classes are mostly mechanical brakes. Now, this can be divided into two parts. One is radial brake. Radial brake, it means that the force, normal force is applied radially. So, here we use few things, drums, drum type brakes or cylinder type brakes. Now, if you look at the cross section, so for example, this is the part of the drum and we apply the force radially. So, force is applied radially. Now, the force may be applied internally or externally. If we applied internal force, then we apply force from here. Now, this is the drum, force applied here. So, this is internal and radial, and if we apply force from outside, so this is external force, externally braking. Now, depending upon what is the force, what is the member which applies this friction force, we have two situations. One is shoe brake and another is band brake. How does they look like? How does it look like? Let us see. For a shoe brake, here for example, we have this shoe brake and we have normally two shoes. So, these are brake shoes. We apply two brake shoes and apply force over here. So this is shoe type of braking, and there is a friction material. So there is a friction material over here. So there, and this friction material, it causes the friction force. This is mu times F. So this is how a shoe brake operates. There is another brake which is the band brake, which could be explained in the following fashions. Now here this is again the drum, and we have a belt attached over here. So there is a continuous belt and there is a lever. Now because of the friction over here, the two forces T1 and T2 in the band. So this is the band and this is the drum. Two forces are different, and that will provide the resisting torque to this moving drum, and this is given by applying a force P with the lever, with the help of this lever. So these are the rough the operating principles of two kinds of brakes. One is the shoe brake and the other one is band brake. If the force is applied in the radial direction, then this is the radial brake. If the force is applied in the axial directions, then we can have this axial brake, and normally the axial brakes, they are something like this. This is the disc which is moving, rotating with omega, let us say, and we apply with the help of a pad, friction pad. There are two pads, let us say. So this is a pad, and this is a friction material. So therefore when we apply force over here, F and F, then friction force is generated, and that has the magnitude mu times F, and this mu times F will cause the frictional torque, that is a resisting torque, to oppose the motions of this particular disc. So this is axial brake. You see that here the force is applied in the axial directions, whereas in the radial brake the forces were applied in the radial directions. So these are the two important differences between the radial brakes and axial brakes. Now these are the roughly the classifications of brakes, and today's lecture we shall concentrate on the shoe brake, and in the next lecture we shall talk about the band brakes and disc brakes. Then of course the major part of the design goes to selection of the friction material. So we shall be discussing the friction material, etc., and their properties in the next class. So let us devote this class to the design of shoe brake. Now before going to the design of shoe brake, let us see what is the energy dissipated during braking. That means what force should be needed in order to apply to bring the moving part to complete rest or to a lower speed. So let us see, normally when the part is moving, then we have definitely one energy, which is the kinetic energy, and this the change in kinetic energy, that depends upon the part which is moving. Now if there is a translating member, then we have half m, the mass of the translating member, and V2 square minus V1 square. Now this is negative quantity because V1 is greater than V2, because we want the velocity. V1 is the velocity before applying the brake, and V2 is the velocity speed after applications of the brake. So V2 is normally and naturally it is lesser than V1, therefore this is negative quantity. So delta KE is nothing but the loss in kinetic energy of the moving part, and this is translational motions. Now sometimes we have the loss in potential energy as well. So that happens in various cases. For example, let us consider this case. We want to, so let us say there is a pulley over here and a mass is moving down m. Now, and here is this gravitational acting. So therefore, because of the, so this is pulley, because of the gravity, the mass will continuously accelerate. Sometimes we do not want that such high accelerations, therefore we apply braking force over here. So we apply braking force, F braking over here. So and that will reduce the speed. Definitely there will be a change in kinetic energy, there will be a loss in kinetic energy, reduction in kinetic energy. Also, as it goes down, there will be a reduction in potential energy. And what is the change in potential energy? It will be half, it will be mg times h. H is the length through which, the distance through which this mass particle m moves after application of the brake. Now, it is very easy to see that h is nothing but half v1 plus v2 times t. That is, t is the time over which the braking force is applied, and this is nothing but the average velocity v1 plus v2. v1 is the velocity before applications of the brake and v2 is afterwards. So, there is the average velocity is v1 plus v2 by 2 and the net distance is half v1 plus v2 times t. So, this is very easily seen. So, therefore, this is a change in potential energy. Now, what are the other forms of change? Now, in any machine there will be various rotating components. Rotating component means that there may be gears, cams, etc. So, there are various rotating components which will ultimately provide the motion of this body m, and normally a power is generated from a power source, and this power, that is, has to be transferred from the source to this particular member m through various mechanisms. So, all these mechanisms will take part in the motions, and there may be various rotating components. So, if you consider the change in kinetic energy of those rotating members, then we can designate this to be KET, that is translating component, and KE kinetic energy, change in kinetic energy of the rotating component. This will be equal to half I. Now, there may be various such components. So, for the jth component, let us say this is Ij, jth component, and the change is omega 2 j, that is the angular speed of the jth component after braking, this one minus omega 1 j square. This is the angular speed of the jth component before braking. So, this is the change in kinetic energy of the rotational kinetic energy of the rotating parts. So, we have to sum 1 to n, suppose there are n such components. So, this is the overall change in the energy, that is overall change delta E will be delta E, delta Ke delta Ke T plus delta Ke R plus delta Pe. So, this is the overall change in the energy, and that change is to be given by that is, this change has to be observed, this energy has to be dissipated in the form of heat by brakes. So, what will be the braking torque required? That can be easily calculated if you use the energy balance equations. That is, a rotating component, normally we consider rotating component. So, rotating component to apply the braking force. So, here the total change is given, and that is equal to the torque, braking torque, let us say TBR, braking torque, times the total angle delta theta, and this is the total energy. And if you see that this braking drum, that is this drum where the braking force is applied, this is the force and this is mu times F. So, the torque is equal to the radius, the total braking torque is equal to R times mu times F, and this drum was rotating, let us say, with a speed in 1 revolution per second, and after braking it comes to in 2. So, therefore, delta theta is again could be proved that this is delta theta is in 1 plus in 2 times t. So, this is the total angular movement of the disc, and the braking torque is R times mu times F. So, from this we can calculate what is the force required. This much force must be required to reduce the speed of this moving part from V1 to V2. So, if you make these calculations, then it comes out to be very simple, and this becomes F is equal to delta E divided by mu times R, and this will be in 1 plus in 2 t times 2. So, this is the force required to give the sufficient braking actions. So, this is now we have studied the energy dissipated during braking. So, this much of energy will be dissipated in the form of heat. So, if this is too high, then the friction material may melt. So, it is very important that we choose the friction material such that it becomes thermally stable. Thermal stability means that it does not change its property if the temperature is increased. So, that is very important property and has to be taken care of very seriously while designing a brake lining. We shall discuss about it in the next class. So, now you know what is meant by what is required of a braking material. Now, this is the energy dissipated during braking. Now, we are in a position to study the design principles of shoe brakes. You see, shoe brakes here, let us consider this case, that is, this is the drum, let us say, and we apply one brake over here. So, this is we apply so this is the shoe of this brake, and we apply a braking force F. Now, this angle, let us say this is equal to theta and that is equal to theta. So, the net contact angle is theta. Now, if we apply this force over here, then the pressure distribution is not uniform. That everyone can understand that the pressure is not uniform, and it is expected the pressure will be high near the central region. Here the pressure is higher and here the pressure is comparatively low. So, now it is very important task to find out what is the exact pressure distributions. Normally it is taken that the pressure, normal pressure, it is distributed. Now, this is a function of theta, as you can see, theta is measured from this line, we have measured from theta here. So, this is the reference line. So, p theta is, let us say, p1 cosine theta. So, this is roughly the distribution which we take for this case. Now that is very easily seen that at theta equal to 0 it is maximum P1, and at theta equal to at some level here it is little lower. So if you schematically represent the pressure distribution, it looks somewhere here. So the pressure distribution is quite large over here and small and this is symmetrically distributed. The symmetry is not very obvious from this figure. So this is roughly the pressure distributions, and this is function of theta. Now obviously the total force F is equal to the summation of all the forces. Now force is a vector, so we have to have the vector summations. Definitely if you consider a small force, this is the pressure. So if you consider at angle theta, or let us say at a small angle phi, this is the very small segment delta phi, d phi, small segment, over which the net force acting is equal to the net force acting over this part is equal to p theta. If the radius is r, then d theta or d phi, then p is a function of phi. If you can write down phi this way, but let us take this angle to be not phi but theta. So at angle small theta, we have to differentiate between two things. Here the theta 1, and it goes from minus theta to theta, but I have taken a small element delta theta at an angle theta from it. So while taking the integrations, we will have to make sure that the two limits are taken properly. So the force per unit length of the drum, that is, if the drum is taken to have unit length, then the net force on this particular area is p theta r d theta. Now of course F is nothing but the total force along the x directions. So if this is x axis, this is y axis, so the net component is here, this angle is theta. So therefore the net component is p theta r d theta cosine theta. So F is equal to p theta r d theta cosine theta, and we have to integrate then from minus theta to theta. So this is satisfied. Now if you make this integration, then it comes that when you make this integral, then what you find is F is equal to minus theta to theta, then this is p1 cosine square theta r d theta, and this becomes p1 by 2, then 1 plus cosine 2 theta, so 2 theta plus sine 2 theta. So this is the n times r. So this is the value of this integral. Now what is the friction force? As you see, on this particular small element, if this drum rotates in this direction, then the friction force here is P theta. So, this is friction force. Friction force will be equal to P theta r d theta, and the net torque is equal to this times r, and we will have to integrate from minus theta to theta. So, this is the total frictional torque. And if you consider that this, instead of this distributed friction force, if you consider this friction force acting as a concentrated force, then it must act over here, because the concentrated force due to this pressure is acting along this direction. So, friction force, concentrated friction force must act over here, and the value of the concentrated friction force is that F friction times R, because they should give the same amount of frictional torque. So, when we use this and find and substitute in place of P theta the value P1 cosine theta, then it becomes twice sine theta. So, twice r square sine theta divided by r. So, therefore, it becomes Fr becomes then Fr then becomes is twice r P1 sine theta. Now, what we see is that the normal force is F, total normal force, total frictional force is Fr, and of course, we have forgotten this important thing mu. So, therefore, this is twice mu times twice r P1 sine theta. We must remember that the total friction force is mu times this force acting over here dP. This is the friction, this is the total force on this area, and frictional force is mu times that. This is due to the Coulomb's law. So, therefore, this is the total frictional force, and if you write down in a more concise way, it becomes something like this, that is F is equal to total normal force is equal to twice P1 R, and this is I am sorry, this was half. So, not twice, twice theta plus sine 2 theta divided by 2, and F friction force is equal to twice P1 R mu times sine theta. So, if you divide this total frictional force, that is this Fr, the significance is that this is the equivalent concentrated force which will apply the same frictional torque. So, this divided by F, this gives the equivalent mu prime is the equivalent coefficient of frictions. This is not equal to mu, as you can see, and this becomes mu times a factor, let me write down, mu times a factor 4 sine theta divided by 2 theta plus sine. So, this is the equivalent coefficient of frictions due to the distributed nature of this force. So, we see that mu prime is not equal to mu, but multiplied by this factor, and this factor is greater than 1, as you can always see. What thing we can check from here is that at theta tends to theta tends to 0, that is a very short shoe, then this becomes mu prime is almost equal to mu times, this is 4 sine theta is almost equal to theta, and this is 2 theta plus Sin 2 theta is almost equal to 2 theta. So, therefore, equal to mu. So, for a very small angle mu prime is equal to mu, and theta pi by 2, it becomes mu prime is equal to 4 mu times 4 divided by, this is 2 times pi by 2 and this is 0, therefore, this is divided by pi, and this is about roughly equal to 1.3 mu. So, if you increase theta from 0 to pi by 2, it increases from this factor increases from 1 to 1.3. Now, it could be plotted. Normally in handbooks you can see those plots, and from these plots what could be seen, that if you plot this is theta and what is mu prime by mu, this is that particular factor, it starts from 1, then 1.05 and so on, and goes to, let us say, 1.3, something like that. So, this one so it goes somewhat like this, and what we see here, that for theta less than 30 degree, if this is 30 degree, then this factor is less than 1.05. So, this error is, if we the change is less than 5%. So, we can ignore that, and if this angle of contact is less than 60 degree, normally this is the thumb rule, that if 2 theta, that is the angle of contact of the shoe and the drum, it is less than 60 degree, then we can take to be mu to be equal to mu prime, and we can concentrate, we can say that the force is entirely concentrated. So, now we know what is the friction force, what is the equivalent coefficient of frictions, and while designing such shoe brakes we should use the equivalent coefficient of friction. Now, let us come to the brake again. This is the brake, and we have a shoe over here. So, this is the brake shoe, and here we have the friction material. This is the friction material. So, this is the drum, this is shoe, and this is the friction material, and we apply force over here. Okay. Then this force is applied sometimes by means of lever. So, it is not possible, it is not generally force is not generally applied directly here, but it is applied by means of a lever. So, lever is arranged somewhat like this. So, this is a lever, but this point is a fulcrum point, and we apply force directly, not here, but on this one P. Now, this friction force is acting over here, and this line of action of this friction force may or may not pass through this fulcrum point. So, let us consider that this does not pass through the fulcrum point, and there is an offset E between the two lines as I have drawn here. So, if you look carefully into the or study the free body diagram of this lever, what we can see is the following thing. That is, this is the lever, we have P applied here, and this is the fulcrum, and let us say this friction this force is acting here. This is the friction force F, this is the force, normal force, and the friction force, because now the drum is now the drum is rotating in the clockwise direction, let us say omega, and therefore this friction force on this shoe, let me not take this drum along this, so let us take the drum instead rotating along this directions. Therefore on this shoe, on this drum, the friction force mu F acts over here, and similarly on this lever the friction force will be mu F over here, and there is an offset E between these two lines of actions. Now if you write down the moment equations about point O, what we can see, now we can write down this distance, let us take this distance is L, this distance let us say A, and this is E. So the force equilibrium equation will be equal to that is minus P times L plus F times A, and here plus mu times F times E. This is must be equal to 0, and we have P equal to F times F by this is equal to F by L and A plus mu times E. So this is the relation between P, F, E, A and mu. We now see that this P is now increased, because E is, if E is taken in these directions, then P is increased, because A plus mu E by L. So this is the factor. Now if we take E to be negative, then what happens? That is, consider the situation where this line is falling somewhere here. Let me draw it in a different figure. What is expected is that this friction force is acting over here, mu F, this is the E and F and P over here. So in that case, what we see that in this particular situations, if we write down this equation, then it becomes not positive but negative, and we have not positive but negative over here. Now what is expected, that if A minus mu E is less than 0, that is if E is greater than A by mu, then what happens? Then P becomes negative. F cannot be negative because F is the normal force, and that must act on this lever. So if E is greater than A by mu, then P is always negative. That means we have to apply the force in the other direction if this situation occurs, and this is the case of self-locking system. That is, we have to, in order to disengage the brake, we will have to apply this force. So this force, so this friction acts in such a way that it automatically locks itself, and we have to give opposing force in order to disengage the brake. So, this mechanism, this is the self locking effect of the brake. Remember that this is the case for the self locking effect. If E is in that in the negative sense, that is in as the situation is depicted over here, E is in this line of action is towards the left, and E is greater than A by mu. Now, this is not desired, because we have this case that the brake locks itself, and this is applied normally in case of backstop of any rotating machineries. Now, what happens that in a rotating member, if so, this is the self locking of the brake, and we want to avoid that. We do not want that, but sometimes it is used in the backstop of rotating parts. Now, before discussing that, we have to remember that in this situation taken over here, the drum was moving in the counterclockwise direction. If the drum moves in the clockwise direction, then again this entire thing changes. Now, this friction force, if the drum moves in the clockwise direction, earlier it was anti-clockwise, if the drum moves in the clockwise directions, then we have this friction force in that direction, mu f. So, the entire analysis changes, and whenever it becomes self locking in for the counterclockwise situations, it cannot become self locking in the clockwise direction of rotations, and if it is non self locking in the clockwise directions, it may or may not be self locking in the counterclockwise directions. So, this advantage is taken care in the backstop of rotating parts, where we want to stop the rotations of any member in the opposite directions. What we have a self locking brake in the member. So, whenever it tries to rotate in the opposite directions, then the self locking devices will set on or act, and it stops the moving part automatically. So, this can be taken care of in a backstop of rotating part. So, what we have, we must have P as small as possible. So, therefore, we need to consider this offset. If the offset is 0, then P is taken directly by the lever principle, that is P times L will be F times A. But if the offset is chosen properly, then even a larger mechanical advantage could be used, and if the mechanical advantage is gained, then we call this self-energizing of the self-energizing actions of the brake. So, we need a self-energizing brake, but at the same time we want to avoid this self-locking of the brake. Now, this is roughly the principle behind the shoe brakes. Again, what we can see that we have applied now we have applied the force only in one direction. We have there is a shoe here. So, we have applied force in one direction. Then what happens to this drum? Drum also, if you draw the free body diagram of the drum, there will be one torque, frictional torque acting over here, as well as there will be a force in one direction, force F in the drum, and that force causes the bending stress in the shaft which contains this drum, because drum will be taken on a shaft and a bending stress is developed in the shaft, and a bearing. So, the bearing will have to support this bending stress. So, this is not desired. We want do not want to overload the bearing. Therefore, what is done normally, there are two similar shoes and these forces are applied. So, now there is no bending stress developed in the shaft containing this drum, but the friction force is developed. But now we can see this friction force is such that the frictional torque is now double. So, it has increasing braking efficiency or braking force, as well as it does not introduce any undesirable bearing stress or bending stress in the shaft. So, this is normally what is done. Now, there are various ways of applying similar force to this brake, to this drum, and in a book you may see various appliances or various ways in which this kind of these two similar forces, equal forces could be applied, and I am not going to discuss that. What we can discuss now is what is known as the another form of the shoe brake, but this is very much useful. So, here this is the drum and we have two shoes over here. Now, this is one shoe, this is the fulcrum, and there is another shoe and there is a spring, let us say, so there is a spring. So, this will normally be disengaged, and we may have one cam. There is a cam which when rotated will push these two shoes. Now, these are two shoes which contain this lining here, this friction lining, and if we rotate this, then of course two forces will be developed, one Q and let us say Q, two equal forces developed over here. Now, what is the pressure distribution? Let me draw it here. Let us remove this. Instead, there are two forces, Q and Q, and this is this lining. So, whenever we apply this force, this pressure develops. What is the distribution of this pressure? Distribution of this pressure is can be seen as follows. When this rotates, that is when this brake, suppose let me draw this part in a little bit. So, this is the part this part, and we have a brake shoe over here. This is the fulcrum, and there may be a lining. So, when this rotates, then of course it goes to some position. Here we see that there will be more deformation here than here, because now it is rotated about this point. So, somewhat like this. So, the deformation is more over here, and therefore, the pressure will be more on this face. Now, if you see that the deformation is more over here, then we can find out what is the pressure distribution as follows. Let us consider a small element here and small thing, let us say gamma, we rotate this. So, therefore, this deformation is could be seen as, this is the center, if you can consider. So, this is the center, and this distance, let us say distance A, and if you consider this angle to be theta at any point, angle theta, then what could be proved, that the force distribution here is P theta will be a function of sin theta, because it can be proved from the geometry that if the rotation is gamma, then the pressure developed will be equal to this deformation over here. So, radial deformation is proportional to sin theta. So, P theta is a function of function of theta and is equal to P1 sin theta, and this one will be equal to P max sin theta divided by sin theta max, and P max actually is depends on the lining of this brake, and it depends on the friction material. We cannot have any P max, this will be governed by the property of the friction material. So, this is the distribution P theta, and with this distributions we can find out what is the force required Q, because we know that this is the P theta. On this small element there will be this P theta, and this is acting radially. Therefore, if we take this moment, the net moment of this normal force, P, let us say M1, this will be equal to P theta R d theta small area, that is this is the force, times this length, and that is equal to A sin theta times A sin theta, and this is from theta 1 to theta 2. So, this is the net moment over here due to this force. The net moment due to the transfer, this is the normal force. The net moment due to the friction force can be found out if we consider this friction force to be, so this friction force here is P theta times mu and R d theta. So, this distance is again R into, I am sorry, this is R minus A cosine theta. So, this is the lever arm which could be multiplied to this force and find out this m theta, that is due to the moment due to this friction force. Then we can take the moment about this point and find out what is Q. This is roughly the design procedure how to find out Q. So, the main thing is that the distribution of this P theta, which is proportional to sin theta. So, this is roughly the way how a shoe brake, the friction forces etc. of a shoe brake is analyzed. We shall discuss that of the band brake and other kinds of brakes in the next class, but I suggest that you look at some books and try to understand how the friction force is analyzed for this kind of shoe brakes. This is internally expanding shoe brakes, and similar analysis could be done for the externally expanded shoe brakes also. We are not going to discuss that, rather we should discuss the band brakes and other types of brakes in the next class. So, this is all for today. Thank you very much. Dear student, let us begin the lectures on machine design part 1. This is the lecture number 40 and the topic is design of brakes. This is the concluding part of the lecture on the same topic. Now in the last lecture, that is in lecture 39, we have discussed how to get the pressure distributions or how to get different forces in a type of brake which is known as shoe brake. And there are few other brakes which we are going to discuss today. But before that, let us go to the shoe type brake again and discuss something very quickly, the internal or external shoeing arrangement. So basic kind of shoe type brake can be taken as, say this is say the drum, and we have the shoe here, brake shoes, there are two symmetrically placed levers, so this is the center of the drum, and at symmetric angle there are two levers, and on them there are these shoes. So there are friction material symmetrically placed again. This is internal radial shoes, and the force is applied here by some mechanisms, and then it it rotates, these two calipers rotates about these two hinges, and then the friction material gets pressed and it develops the frictional torque. Now if we take these two angles to be theta 1, we measure this angle from this point, let us say this is theta 1 and this one is theta 2. Then the pressure distributions, of course I have not discussed how to get the pressure distributions, but the pressure distribution looks something like this. This is the pressure distributions. So at any angle theta, now measured from this point, this line, theta is measured from here. So at any angle theta, it is P max